Good morning, all. My name's Dick Dunn, and I'm the National Bridge Preservation Rep for GPI. And so this session is titled Stuff Too Good to Miss, because we wanted to get people jazzed up a little bit for the last day, last morning. And what I want to recommend that next year when we do this, we have walk-up music. So Chris could choose his walk-up music before he comes up here, you know, something like that. So, but first up, we're going to have Chris talk about cathodic protection case studies. So come on, Chris. Kind of tell who you are.
Thank you, Dick. My walk-up song from Kentucky, so it's probably be country music of some sort. But thank you, and thanks, Dick. Thanks to the Midwest Bridge Preservation Group and to South Dakota. You guys putting on a good show as always, and I really appreciate the opportunity to speak to the group here today. I am going to talk about cathodic protection bridge studies, and in the amount of time we have, it's kind of compressed. I'm going to try to go through 3 different examples of where cathodic protection has been used in the states that are covered by the Midwest region. So we're going to go fairly quick. The first thing just to talk about, here's pictures from different states. You guys recognize these. Some of these are just corrosion that have occurred because of leaking joints. That's a very common thing. You're going to have corrosion from leaking joints or from snow being pressed up against the side of structures, very commonly. And what we're talking about, just to be clear, is reinforcing steel corrosion. Here's an example of a structure where the DOT actually painted, and so they would try to provide a barrier coating, but you see there was some ongoing corrosion underneath of the coating. So the coating itself may have helped, but it didn't really solve the underlying corrosion issue, which had already been initiated. And here's another example. This is a shotcrete repair. You can see the welded wire mesh that's been put into the repairs, and they didn't chip behind the bars and do a lot of good practices there, and they didn't really address the corrosion issue with the repair. And this is just an example of a typical kind of, this is in Kentucky at the Sherman-Minton Bridge. So just examples, and you guys will see these every day. So what I wanted to focus on is one of the solutions potentially to help deal with structures that actually have problems at this point, active corrosion. And based on the time we have, I'm not going to go through a whole corrosion cell and everything like we typically do, but just real quickly, what is corrosion? Corrosion is an electrochemical process. In the areas where you see the rust is the anode. That's where the steel is giving up electrons. It's starting to revert back to its original form before steel was created. And for every corrosion cell, there's also a cathode. And the cathode is basically the side of the corrosion cell that's not rusting. And it's actually being protected by the current. There's electrical currents, electrochemical processes being generated by the anode. And the good thing about concrete is that concrete itself creates a buffer to this corrosion cell. So as opposed to like exposed steel, the alkalinity of the concrete and even just the density of the concrete can delay the onset of corrosion and be a beneficial, but eventually the concrete loses out when you have the right environment. So what is cathodic protection? Cathodic protection is an electrochemical process. It's basically using the same ideas of the corrosion cell, but using it in a proactive means in order to provide direct current to the reinforcing steel, either by an impressed current system, an outside power supply, or by the use of sacrificial or dissimilar metals, and that's galvanic protection. And once you're trying to make all the reinforcing steel the cathode or in a non-corroding state by using these artificial anodes. And so the idea is that you're either going to slow down or stop corrosion with cathodic protection. So it's just another example of a structure, leaking joint, substructure corrosion. So, there's options. This is a design guide that's available, but talks about options currently available for actively corroding structures. I'm going to talk about cathodic protection and probably focus a little bit more on galvanic, but you also have this sister process called chloride extraction. If you guys may have heard that, we've been doing that for over 30 years, that's also an electrochemical process that it kind of does the same thing with the temporary treatment. So that's just a real quick on the background. Applications, case studies, these are just showing you like real life examples that you might be able to apply to your own state. Ohio DOT, we have done a lot of work in Ohio through the years on their abutments. And they have these slab bridges where you see the leaking joint right on top of the abutment, and you always start to see initial spalling around the top from corrosion of the reinforcing steel. And the idea here is that we ended up going, helping them to design a process that we call galvanic encasement of the abutment. And I'll just show you some examples of this. So this isn't back around 2005. I couldn't remember the exact year, but somewhere around that time frame. And you see the conditions of these, and some of them can be fairly severe on their corrosion. So in the early days, they were just doing some patching. Then they started doing some patching with some of the original hockey pucks. You guys have probably heard about those, just to provide some protection to the halo effect kind of situation. But in reality, this was a widespread problem, and it really needs a widespread solution. Using a few anodes here and there is not really fundamentally extending the life of this abutment. And so the idea was that what can they do to basically structurally affect the abutment from a structural and a corrosion protection standpoint in a very positive manner. And so the idea here is that they would basically put a 6-inch face on the abutment with new reinforcing steel and what they called distributed anodes, or these long anodes. So this is one of the projects that goes back to 2005. Same kind of situation as the other pictures that you saw. The first step here is to basically do your removal of spalls or delamination. So you got to remove your unsound concrete. But because you're providing a cathodic protection system in conjunction with the repair, a lot of times they're just removing unsound concrete. They're not aggressively extending the areas of repairs or what have you. Removing all the chloride contaminated concrete, you can leave that in place. And then this is showing the galvanic encasement being installed. So you see these tan long strips. These are distributed anodes made out of zinc. They're alkali activated based on the same technology we've been using for 20 years. And you see dowels into the facing, new anodes going across. And then in the case in Ohio, they like the epoxy coated bar, so use epoxy coated bar in the facing. A lot of places will just use black bar, and we'll just tie the black bar in with the galvanic system, so the black bar is also being protected by the galvanic anodes. And then you have the forms installed. This was an early use of self-compacting concrete to do a form and pour repair. And this is because this is one of the first jobs that ODOT did. They wanted to monitor, so there's a whole monitoring station that's been installed here. So concrete's been placed now. The forms have been removed. And then after that, they basically used a coating just on the surface to make things look better and maybe provide a little extra protection. So that's it's a very, very solid, kind of repair method. You're not just patching, you're providing a more global solution for the entire abutment. Now, fast forward, this is 17 years later. You see some leaking and efflorescence, but overall, the structure is still in really good condition. And the good thing is because of the desire for the ODOT to monitor the system is that we have lots of data. And so this goes back to 2005, and it's probably a lot of numbers that you probably don't understand unless you're really heavy into corrosion. But the main point here is that you might have heard of NACE. NACE is part of AMP now. The cathodic protection requirement to say a structure is fully cathodically protected is that it has to have a depolarization of greater than 100 millivolt shift. And you see all these numbers are significantly over 100 millivolts. So these anodes are significantly providing a high level of protection to the embedded reinforcing steel. So it's a really good example of long-term durability with a lot of monitoring. So this is another interesting aspect. The options that they were looking at is like replacing the abutments, and if you start looking at, or maybe even replacing the structures. So they were able to do these repairs with minimal impact on the traffic. It's kind of a one-step repair and protection. These are some numbers from the DOT from the original project. The rehabilitation of the abutment versus rebutment replacement and shoring versus the replacement. And after 17 years, it's still performing well. And this, in fact, just this week, this was awarded an award from the International Concrete Repair Institute for longevity of repairs. So a nice little example of something that's practical that you guys can maybe look at. You could use the same kind of technique for columns. We've done it, anything where you can build it out and use some new reinforcing steel you can use as a galvanic encasement. All right, so next thing I'm going to talk about is a more substantial project and really more recent is the repair of 3rd Avenue Bridge, historic bridge in Minneapolis. And this is a very substantial project that's just now wrapping up. And so you see some of the original structure as it's under construction. You see some of the details. I see the cost. I'll just let you guys look at that. More recent inspections determined there were substantial repairs imminent. And the goal here is a 100-plus-year-old bridge seeking 50-year service life. When I wrote that, I was like, this kind of sounds like Match.com, but we can help maybe match people with problems and solutions or something like that. Anyway, that just came to my head here. So what we're going to focus on is not the whole project, because there's a whole, we could talk about that for 2 hours probably. We're just going to talk about the arches. And the arches here did not use conventional reinforcing steel. They used the Milan kind of steel framing system. So basically it's a steel frame structure effectively that is filled with concrete to create the structure itself. And the problem that they have over all these years is just leaking from the top down onto the substructure, and they really had severe corrosion of the corners, and particularly around these angles on the corners. And you see some of the cracking showing in areas of delamination, etc. And there was some isolated corrosion even on the metal pieces that were in the intermediate areas, not on the exterior. So on this project, kind of walk through, identify the unsound concrete. You see it all clearly marked out with bright red paint. See the underside of the arch and how severe the corrosion. And because this was historic, they wanted to maintain as much as they can the original structure and original appearance. So as with most concrete repair projects, you need to remove the unsound concrete. You see the removal. And as part of this, it doesn't have as much to do with the corrosion, but it's just interesting. They used a wet shotcrete material. I don't know if you've ever seen this in action, but you kind of see it being sprayed on. You basically have the wet mortar being flowed through the nozzle, and you have a burst of air that's spraying it onto the surface. And then the nice thing here was that because the historical, they were trying to recreate the board form finish as well with the shotcrete. So you had to have some skilled technicians to do that. So from a corrosion protection standpoint, in addition to the repairs, how do you get this structure to last for the 50 years? Because the repairs themselves aren't going to really solve the issue. And so there's a number of different techniques that were utilized, and I'll talk a little bit about these. So here you see the original steel. It's been coated with a protective coating where it's been exposed. And then they also used new steel around that, because there's no rebar in this structure. It's just the steel angles. And so a lot of that steel is still embedded in the chloride contaminated concrete. And so in this situation, use a combination of these, just the long distributed anodes, similar to what we showed for the ODOT abutments, but they basically follow the arch, and that's designed to provide all the protection to the uncoated areas of the steel. So the areas that may have holidays in the coating, but also the parts of the structure that's still embedded in concrete. And then at these interfaces where you have the new and old concrete, that protection was supplemented with the use of some of the XP or the smaller anodes. And you see here how the anodes were connected. They're not connected into the reinforcing steel like you typically see by turning the tie wires around. They're actually connected to a self-tapping screw that's been drilled into the structure. And so these are designed to give supplemental protection at that interface. Now, as part of this also, they did a full corrosion potential survey. So any of the areas where you didn't have the existing damage, but you were detecting active corrosion on the corners, they proactively installed these custom anodes. They call them two-stage anodes. So this is where the angle was, and you put a pattern of anodes on each side to provide proactive protection. Because as you saw previously, the amount of scaffolding and everything to get onto the structure is substantial. So to take care of not only the problems you see now, but the areas you can detect moving forward was the idea. And these anodes basically utilize a two-stage. They basically have a battery incorporated in with the galvanic anode, so it gets you a higher amount of current to begin with, and they're usually designed for 20 or 30 years of protection. You see them being installed proactively into drilled holes. This is a connection to the embedded steel, and then you have a header wire that kind of interconnects the anodes, and there's a spec for how many anodes you can put per rebar connection or steel connection. So, and then in some areas, particularly around the abutments and some of these staircases they had, they basically use a metallized zinc anode on the surface, which is a whole other kind of surface applied distributed galvanic protection system. And there's the metallizing taking place there. So it's really nice, a real combination of solutions, a lot of concrete repair, a lot of galvanic protection, et cetera. And I'm sure we have some people in Minnesota supposed to have the opening celebration here at the end of the month. So big investment to extend the life of an old historic structure. All right, and then the final thing I wanted to show is something a little bit newer. This is, I mentioned the zinc metallizing as a surface applied kind of galvanic anode. It takes a lot of equipment, specialized equipment and testing or knowledge. Something that has been more recently utilized is a surface-mounted galvanic anode. It's similar to the distributed anodes that we talked about, but the anode is basically cast into a tray, and this tray is applied to the exterior of the concrete. So one thing it does is it eliminates a lot of the drilling that you saw with doing the drill holes for those two-stage anodes. You basically still need to make a reinforcing steel connection, but you'll eliminate a lot of the drilling to embed anodes into sound concrete. So this is a little section that we did, just some minor surface preparation just to remove the graffiti and some surface latents on the concrete. Like I said, you need to make the reinforcing steel connections. And this is one of the early pilot installations. We use different size anodes here, but the idea is that you put a mortar on the back. It's a special mortar that we have that creates the bond between the anode and the concrete surface. And it also is the electrolyte that allows the current to flow from the anode to the reinforcing steel. And once again, this is a project that's been monitored just to understand how these operate. So you see a lot of conduit there, and anodes at different spacing. So it's kind of like a pilot installation. A lot of good information developed out of that. So in normal situations, the anode would be just directly connected, and you would not have to have all the conduit on the monitoring. So I just want to kind of point that out. And this is a remote monitoring system, has a solar panel, et cetera. And just some of the data that's come out of that is really, a lot of here's a measuring temperature. This is a Kentucky. The guys in Kentucky, remember, we had the real cold snap back in December. I think it dropped like 30 degrees in 4 hours in my house. We get the warm summers, and you see the galvanic current density kind of going up and down with the temperature, so they're acting kind of as normal. And then an example of some of the polarization testing is we had embedded reference cells in this, and kind of showing that you're getting the level of performance of the system that you like. Just the last little thing, it's not really a case study, but just wanted to point out that some things have been happening in the industry that you may not be familiar with through AMP, the cathodic protection. AMP is heavy into coatings and other things. Yeah, also have the cathodic protection situation committees. There's a new standard for performance of galvanic protection systems for concrete that's available. If you want information on that, you can visit our website. We have a lot of the information on this, or you can just contact me directly. But one of the main points of this is that it requires the designers to consider the performance of anodes over time, which kind of makes sense, but it never really has been this clearly stated. And one conclusion of this is that, for you guys who are familiar with the small anodes, the amount of zinc does not have anything really to do with the long-term performance of the anodes. So to have systems that you see long-term data that you can use to predict and do performance-based designs is the kind of the future, I think, for that. So thank you. I don't know if we have time for questions or a couple, or sorry, I felt like I went pretty quick, but hopefully you guys picked up a few things there. Of course, Tom would answer.
No, just the challenge with some of the distributed anodes really is life, right? And so that new standard, I would like to look at that a little bit more.
Yeah, for sure. Yeah, for sure.
Yeah, getting that 50-year service life with distributed anodes is a challenge. And so
Right.
Is there a repeat process even on that Third Avenue that was assumed
Right.
for 25 years down the road?
Yeah. So they're probably looking at an active life of the anode somewhere between 20 and 30 years typically. You can design for 50 years. You just have to use more anodes. But in reality, especially for the embedded systems, you're not going to really replace them. Now, that's one of the benefits of the surface-mounted system is like 20 years from now, you could take them off and put another system on. You're not going to do that on a historic bridge. So in that situation, like what ends up happening over that 20 or 30-year period when those anodes are active, it's actually making the structure more passive. So when the anodes actually expire, because they're galvanic, they're sacrificial, the structure is actually in a more passive condition than it was initially. So there's going to be, it's hard to define, but some big, longevity to the protection after the anodes are gone.
All right, let's give Chris a round of applause.
Okay, well, I'll be around. Look, one more question?
Sorry. Was there another question?
Yeah, I had one more if you had.
There was one more question. We got time for one. You almost got beat up by
All right, I mean, it's my lucky day.
I was wondering if you had ever embedded the sacrificial anodes into decks and had any results with that or any experience
Sure.
with that or any comments.
Yeah, no, there's a lot of, that was some of the early uses of anodes is just to extend the life of the repairs. And you see when you do deck repairs over time, they just grow and grow. To be able to slow that down using just some small anodes in the repairs, it's definitely helpful, and we have a long history with that. But once again, if you want a more comprehensive solution, you can use the same kind of galvanic anodes in the overlays and things like that to provide protection to the whole deck. Another option. So just real quick, we did the bourbon draw. A lot of you guys stopped by our booth and had dropped your card in the toolkit. And so I just pulled that on the way up here. Eric Hart. All right, there we go. There we go. Okay, so you can stop by our booth after the session here and pick up your raffle. So thank you guys. Appreciate it. Yeah.
Thanks so much, Chris.